In this lesson, we'll learn about the different types of bolted joints and how their mechanics make them different from each other. It's important to learn this distinction because picking the right fasteners for each joint type is crucial for the performance of the bolted joint. For example, two of the most commonly used bolts are the partially threaded and the fully threaded bolts. Choosing the wrong bolt type in a bolted joint design can lead to the failure of the bolt and ultimately the joint itself. Depending on the types of load supported, the bolted joints can be classified into two types: the tension joints and the shear joints. Each type has a different mechanism and therefore has different design requirements. Some bolted joints may need to support both the types of loads, in which case the joint shares both the design requirements. Now let's look into the mechanism of these two joint types, starting with the tension joints. The tension joints are used for transferring tensile forces between the clamped parts. The external force acts along the axis of the bolt, and as a result, it adds to the existing preload in the bolt. So, the tension in the bolt shank increases beyond the initial preload. It's important to keep in mind that the bolt can experience plastic deformation during operation even if it's within the elastic region during installation. The design requirement for such joints includes proper selection of bolt thread accounting for the maximum external load that it may be subjected to. In case of shear joints, the bolted joint predominantly transfers shear forces between the clamped parts. In this case, the friction between the fastener heads and the components plays a crucial role. The friction force is directly proportional to the preload in the bolt, as the preload is responsible for creating the normal contact pressure between the fastener heads and the components. So, once again, bolt preload is a critical design requirement for the shear joints. If the applied force is greater than the maximum frictional force between the parts, then it results in gross sliding and eventually leads to failure of the joint. Also, in this type of joint, the bolt is under shear loads, so its shear strength is another important requirement for the design. Due to this reason, partially threaded bolts are generally preferred for such joints. In both the examples, we saw how the joints support the external loads, making use of the existing preload. When the bolted joint is operating as expected, it generally maintains a static state, meaning that all the forces are balanced by the reaction forces. When one or more of these forces is not balanced, it's no longer in a static state, and it generally results in failure of the joint. To gain better understanding of this, let's look at the model of a simple bolted joint and see how these forces balance each other out in different joints. Let's take this tension joint and study its forces. The two plates are clamped between the bolt head and the nut. So, compressive forces are acting on them from both the sides. These forces are applied by the bolt and the nut, so they will experience a reaction force in the opposite directions. These two sets of forces balance each other out to maintain a static state. Now, let's fix the lower plate and apply an external force on the upper plate. This force is transferred to the bolt head at its contact with the plate. This will generate an equal and opposite reaction force at the nut. These two forces will balance each other out, and total force acting along the length of the bolt is summation of the preload and the external force. So, the clamp force in this joint has changed. In case there is a failure in the bolt, such as failure of threads, or if the shank experiences excess plastic deformation, then the forces are not adequately transferred to generate this reaction force. So, the external load is no longer balanced. As a result, the system is not in a static state anymore, and at this point, it's considered to have failed to support the external load. One last thing to remember about the bolted joints is the concept of pressure cone. Under the compressive forces acting on the clamped parts, the stresses distribute in the shape of a cone, and this is called as a pressure cone. The shape of the cone depends on the dimensions of both the clamped components and also the bolt specifications. It's important to take this cone into account while designing the bolted joints, especially when there are multiple joints supporting it. If the bolts are too close to each other, then their pressure cones can interfere and increase the stresses in the clamped parts. If they are too far apart, then the pressure distribution can be non-uniform, which is also not desirable, especially in case of pressurized enclosures. With this, we can conclude our discussion on mechanics of bolted joints.